Hi, this is Captain Steve Tarrant from Maine Maritime Academy with another video regarding trim. So in this problem, and by the way, this comes directly out of your book on page 194. It's example number 5. We're going to load a vessel, but the thing is that as we load the vessel, we only want the trim to change. We want there to be a trim change, but we want the draft to change only at one end. Okay, so you can kind of think about this. We might have loaded down to where we want the forward drafts to be, but we want to put more weight on because we're not at our aft drafts yet. So we want to figure out where we can put some weight so that this draft will remain the same here, but this one will get deeper. All right, and so here's the problem. You got a vessel, and in this case we say that the vessel's got 21 foot fore and aft, so this is 21 feet, this is 21 feet. How much weight and at what distance would you need to load it so as to end with a draft of forward 21? That's what we started with here, but an aft draft of 22, 1 foot deeper, which would give us a 1 foot drag. Now in this problem, they gave us TPI, which is 48, and MTI, which is 1035. So let's say this draft is 21 feet. We want it to stay the same. Well, what are we going to do? We want to load this thing, increase our draft aft, but keep this the same. Is that possible? Well, it turns out it is. There is a spot on the ship aft where if I load here, okay, when I load here, I'm going to make the vessel come down. Okay, I'm going to increase the parallel sinkage, which will increase this draft. But if I put it after the tipping center, I'm also going to change the trim such that I'll increase the stern trim and decrease the bow trim. So I want to find the spot on the ship where I can load the weight that the parallel sinkage that will increase the forward draft will be offset by the trim change by having it aft, so that essentially there's no change here. So the instructions for how to do this are pretty similar to one of the problems we just did a few minutes ago. Okay, we're going to have to calculate the parallel sinkage. Parallel sinkage is the difference between the initial mean draft and the final mean draft. Step 2 would normally be that we have to calculate MTI and TPI, but they're already given to us, so we actually can skip these 2 steps. Okay. Now we're going to have to calculate the required weight, okay, to sink the boat to our final mean draft. Okay. So that is going to be TPI times parallel sinkage. So we have to calculate this parallel sinkage. We've given the TPI. We're going to multiply those two to get whatever the weight is. And remember that when you do these problems, first we break it down, load the weight at the tipping center, get down to the mean draft, and then slide it either aft or forward. All right, to determine the distance to put it. All right, so that's essentially what we're doing here. So we're going to calculate the required trim, the required change in trim. Well, the required change in trim change, is going to equal the difference in the initial trim from the final trim. So we're going to have to calculate those, and then at the end we'll solve for D using this formula. Okay, trim change equals the trimming moment divided by MTI. So first we're going to calculate the parallel sinkage. So we need to calculate the initial mean draft and the final mean draft. So the initial mean draft, well, if we're on an even keel, the mean draft is 21. Everything is 21. That's assuming there's no hogging and sagging. Well, what is our final mean draft? Well, we're going to end up with a drag of 1 foot. And we want our forward draft to stay what it already is. So the final forward draft will be 21 as well. If we're going to have a drag of 1 foot, that means the aft draft will be 1 foot greater. Okay? So what's that mean draft? 2106. So we have our 2 values now. Now we're ready to calculate the parallel sinkage. We have to subtract those. We have to get the difference between these two. Parallel sinkage is going to be the mean draft forward in this case minus the mean draft initial, which is 2106 minus 21, 6 inches. We have to add enough weight to this vessel to sink it 6 inches. Once we've sunk it 6 inches, then we'll slide the weight back. So we are going to, by doing that, we're going to increase the forward draft by 6 inches. But wait a minute. If we increase it by 6 inches, we're no longer at 21. If we load the weight back aft, we can change the trim by 6 inches. All right. And that will get us back to 21 feet. So normally we'd have to go to the deadweight scale, but since we're given TPI and MTI in this problem, we don't have to do that. So there are those givens. Now we're going to go to step 3. What's the weight? Well, weight's going to equal TPI times parallel sinkage. Well, we have TPI. There it is, 48. We calculated parallel sinkage. There it is, 6. So in order to increase the draft by 6 inches, the mean draft by 6 inches, we're going to have to multiply 48 times 6. And that gives us 288 tons. So now we'll go on to step 4. This is where we have to calculate the trim change, or the total change in trim. Well, trim change is the difference between the final trim and the initial trim. Or it could be the difference between the initial trim and the final trim. Just make it so that whichever one is larger goes first, so you don't end up with a negative number. Well, the forward initial draft was 21. The aft initial draft was 21. That means our trim was 0. That's not hard to figure out. And what do we want at the end? Well, 21, 22. Our final trim we want to be 12 inches. So our trim forward is 12 inches. Our final trim is 12 inches aft. Our initial trim was 0, so our trim change is 12 inches. Okay? We probably could have figured that out just by looking up here, but that's the sort of the math for how to do that. So step 5, now we have to figure out the distance. We know how much weight we're going to have to add. Now we have to where to put that weight. And this is going to all right. So anyway, so trim change equals trimming moment divided by MTI. All right. Well, again, we can break trimming moment down into 2 variables. Trim change equals weight times distance divided by MTI. Well, we're going to be solving for distance, so we have to rewrite this formula, solving for D. D equals trim change times MTI divided by W. So 12 times 1035 divided by 288 and 43. And we have to put it aft so that we can bring the drag, we can increase the drag aft. If we put a weight of 288 tons at a center of gravity 43 feet aft of the trimming center, so this might be 33 feet. This might be a ballast tank from 33 feet to 53 feet. Well, the center of that, the center of gravity, is going to be at 43 feet. Okay, so if we ballasted down at 43 feet, the forward draft would remain the same, and all of the draft changes would happen at the stern drafts. Okay, there's a spot like this for up forward, where if we had, instead of putting it back here, we put it up here, we could have kept the stern draft at 21 and increased the forward draft. Well, now that we've solved that problem the long way, there actually is a shortcut that we can use. So here's how the shortcut works. There's a formula for it. The distance that you'll load, okay, to keep the draft the same at one end will be 2 times the MTI divided by the TPI. So if you do that, that's 2 times 1035 divided by 48. We were given 1035 and 48. And distance is 43. You can see that. It's the same distance. Well, if we want to keep the trim, if we want to keep the draft the same forward, we would actually put this 43 feet after the trimming center. If, however, we wanted to keep the aft draft 21, we would put it 43 feet forward of the trimming center. That's an easy shortcut. And in fact, this situation exists. You have this possibility of changing the trim at one end only when your parallel sinkage is half of your change in trim. Remember, this formula only works when you're going to keep the draft constant at one end and change it at the other. Can't use this formula if you're changing the drafts at both ends. Okay, thanks.